Hello everyone. So today I'm back with one more video. So I was teaching thermodynamics in my last session, and today I will do the last lecture on the thermodynamics part 1 series. So I was discussing about the mathematical expression of work done in reversible process. Today I'll discuss the mathematical expression for work done in irreversible process, and that's the end of this thermodynamics part 1 series. Okay, after that I will start thermochemistry and then thermodynamics part 2. Okay, so let's get started. Let me share the screen. So if you do not remember what is irreversible process, please do watch my first lectures where I have mentioned what is an irreversible process. So in brief, irreversible process occurs against a constant opposing pressure without the restriction of occurring in successive stages, with in each step happening equilibrium. That's the criteria for reversible process. So in case of irreversible process, it is a single step process. It is not a multi-step process. Okay, and this occurs against a constant opposing pressure. Okay, so please do watch my first lecture series in this thermodynamics, where I have mentioned everything in details about the irreversible process. So what is the general expression for work done in irreversible process? That is W. I'm writing it as irreversible is equals to V2 into V2 minus V1. Okay, so where suppose a gas is expanding its volume V1 to V2 against the constant opposing pressure P. Okay, P2. So for irreversible isothermal process, so T is constant for isothermal process. T is constant. So P2 will be equal to nRT by P2. Similarly, V1 will be equal to nRT by P1. So we are assuming this as ideal gas. We are not talking about a real gas, okay? So what will be W irreversible isothermal is equals to P2 into P2 minus V1, which is P2 into nRT by P2 minus nRT by P1. Okay, so we can take this nRT common and it will be 1 minus P2 by P1. Okay, so this is the mathematical expression for work done in case of irreversible isothermal process of an ideal gas. Okay, so now we'll talk about irreversible adiabatic process. So irreversible adiabatic process So if you do not know what is isothermal process, what is adiabatic process, I have discussed in details about those in my previous lectures. So please do watch that. So this expression of W irreversible adiabatic is equals to NCV T1 minus T2 prime. Okay, so this is coming from the first law. 0 is equals to du plus w. I have done this multiple times. This is the mathematical form of first law in case of adiabatic process. So w will be equal to minus du, so minus ncv dt. So I'm just writing this over here. Okay, so this is coming from the first law. So T1 is the initial temperature and T2 prime is the final temperature. So adiabatic process, it occurs at the cost of its own internal energy. Okay. So now I will derive the expression for T2 prime, the final temperature. Okay. So what is T2 prime? So let's start from the first law. W is equals to minus du. For irreversible adiabatic process, because Q is equals to 0. So what is W? W is equals to V2 minus V1, okay, is equals to minus NCV T2 prime minus T1. I have already discussed about all these expressions. What is expression of W? What is expression of du? So if you do not know about this expression, please do watch my previous videos. Okay, now we'll replace V2 from this ideal gas equation. PV is equals to nRT, or P is equals to nRT by P. So this will be P2 into nRT by P2 minus nRT by P1. So this is equals to minus NCV T2 prime minus T1. So now let's cancel all of the n's. So we will just write R into T2 prime minus T1 P2 by P1. This will be equals to CV into T1 minus T2 prime. Okay, so I have just reorganized things and I have got this. If you do not understand this, please let me know. I can explain later on to you if you do not understand this, but this is simply doing some position exchange over here and canceling the both side terms. Okay, or so you can write T2 prime into R plus CV is equals to CV T1 plus R T1 into P2 by P1. Okay, or T2 prime is equals to CV T1 plus R T1 into P2 by P1 divided by R plus CV. Okay, So now we can write this as T2 prime is equals to CV T1 plus R T1 P2 by P1 divided by Cp, because it was R by Cv, and we know that R plus Cv is equals to Cp, so I have only written Cp instead of R plus Cp. So this we can write T2 prime is equals to T1 by Cp into Cv plus R P2 by P1. Okay. So this is the expression of the final temperature in case of irreversible adiabatic process. Okay. So now we will discuss about the work done in irreversible cyclic process. So I have already discussed about cyclic process for multiple times. Please do watch my previous lectures if you do not know what is a cyclic process. So let me just draw a small diagram quickly. So this is V1, this is V2, and there is a piston over here, P1 to P2, then it will come back to P2 to P1. So first it will go from P1 to P2 and then it will come back. Okay, so this is a cyclic process where a system starts from initial state and reaches final state and then again come back to the initial state. So this is W1 and this is W2. This is work done in the forward process and this is work done in the backward process. Okay, so work done in forward process that is W1 equals to P2 into V2 minus V1, and work done in backward process W2 is equals to P1 into V1 minus V2. Okay, so we can write this as minus P1 into V2 minus V1. So you can see from here W2, the magnitude of W2 is greater than magnitude of W1 because P1 is greater than P2. So W2 magnitude will be greater than W1. So W is equals to W1 plus W2. So we can write P2 V2 minus V1 plus. So this is a plus W2. I'm just writing the expression minus P1 V2 minus V1. So this will be V2 minus V1 into V2 minus V1. Okay. So this will be a negative term. This will be a negative term as P1 is greater than P2. So this will be a negative term. That means work is required to bring the system back to its initial state from the final state. Okay, the system cannot be restored to the original state without the aid of an external agency. That is why it is called irreversible. So now I will draw the diagram for this. So I'll draw the PV diagram. Okay, so this is P, this is V. Okay, so need to draw the diagram. Okay, so here the W1 is equals to P2 into V2 minus V1, the work done in the forward process, and this is denoted by the area of BCDEB, this one. So this is denoted by this one, BCDEB. And W2 is equals to minus P1 V2 minus V1. This is denoted by the area of ACDFA. ACDFA, the whole thing. Okay. So now what will be the W? W is equals to W1 plus W2. So if we add these two areas, it will be the area of A, B, E, F, A. A, B, E, F, A, this one. So this will be the total work done. As we always know, W2 magnitude is greater than W1. So we can write this in terms of PV diagram like this. Okay, so this is work done in case of irreversible cyclic process, that will always be negative. Okay, now we will compare the work done between reversible and reversible process. Okay, so I have already derived the mathematical expression for reversible process, the work done in reversible process, and now I have derived the work done in irreversible process. So we'll compare these two works for reversible and irreversible process. Okay, so I am taking isothermal expansion of an ideal gas. Isothermal expansion of ideal gas. Okay, to make everything simple, we'll just compare these two process, the work done in these two process, and I'm taking isothermal expansion of an ideal gas. Okay, so what was the expression for reversible process, isothermal process? I have derived it in my previous lecture. Please do watch that. So the expression was RT ln P1 by P2. Okay, so we can write this as RT ln 1 plus P1 minus P2 by P2. Okay, we can write P1 by P2 like this, and we can assume this is a very small quantity, P1 minus P2 by P2. So this is an approximation. Since this is very small compared to P2, we can write this as RT into P1 minus P2 by P2, because P1 minus P2 by P2 is not a large quantity, it's small. Okay. So we can write this. We can write this as an approximation. And now, just now, we have derived the expression for the irreversible process work done. That was P2 into V2 minus V1. And we have considered this to be a isothermal expansion of an ideal gas. So we can just replace V2 and V1 with the ideal gas equation. So it will be RT by P2 minus RT by P1. Okay, so we can write this RT into 1 minus P2 by P1. Or this will be equals to RT into P1 minus P2 by P1. Okay, so as you can see, I have tried to write in similar form for in case of reversible process and irreversible process. Now, obviously, P1 is greater than P2. So definitely W reversible will be greater than W irreversible. Okay. So from these two expressions, since P1 is greater than P2, so W reversible will be greater than W irreversible. Now we can draw this mathematically. Okay? And for the PV diagram, I'll draw this. So this is P and this is V. So we can draw this. So this is V1, this is V2, this is P1, this is P2. Okay, so this is reversible process and this is irreversible process. So we can draw a PV diagram for the work done in case of reversible and irreversible process. And as you can see from these two areas, this reversible process, it has a big area, like it is covered by the whole thing. And irreversible process, this is only this area, this rectangle. So you can see from this diagram that the area for the reversible process is greater than the area for the irreversible process. Area for reversible process is greater than the area for reversible process. So this area is denoted for the work. So the work done in reversible process is greater than work done in irreversible process. Okay, so this is the PV diagram for that. Okay, so I'm mostly done with all of the sections for thermodynamics part 1. So I'm closing this thermodynamics part 1 series today, and I will begin thermochemistry and thermodynamics part 2, the second law, entropy, and many more things in my next videos. Please do watch that. Now I'll just, I want to summarize few mathematical formulas that is needed often to solve the mathematical problems in physical chemistry. So I will summarize a few key formulas for the thermodynamics part 1, which you will need to solve a mathematical problem. Okay, so number 1 is work done is equals to P opposing into dV. dV is the change in volume. This is the formula number 1. And then obviously Q is equals to du plus W. This is the first law of thermodynamics. And then H is equals to U plus PV. So H is the enthalpy, U is the internal energy, P is pressure, V is volume. Okay, and then Cp, this is the molar heat capacity at constant pressure, and this is del H, del T, P. And CV, this is molar heat capacity at constant volume, del H, del T, V. And then the change in enthalpy and the change in entropy. So du, the change in internal energy, this is equals to NCV dt plus del U del V T dt. Okay, and dH is equals to NCP dt plus del H del P T. Okay, so these are few mathematical formulas from the thermodynamics part 1 series, which is often needed to solve mathematical problems in physical chemistry from this thermodynamics part 1. Okay, so I have written all these summaries. So this is the end of thermodynamics part 1 series. I hope you guys have enjoyed it. If you have any question, please do write in the comment sections. If you do not understand anything, if you want to solve some new problems or you have some other queries, please do write in the comment section so that I can take care of it. Okay, and please do like, share and subscribe to my channel. This encourages me to make new videos. Okay, so bye bye for today.